Determine the current waveform. Okay. So this is the voltage waveform. Okay, and we need to find the current waveform. Okay, so our V of t is given as 24t by 6 into 10 raised to the power minus 3. So it's the curve is given, and similarly, you can also find this curve using slope formula, which is y is equals to mx plus c. Okay, and then 0. Okay, so from 0 to 6, its slope is 24 by 6 into 10 to the power minus 3t. From 6 to 8, this is the slope, and from 8 to onwards, the slope is 0. So we need to find out I of t. So as we know that I of t is c dv by dt. So for each interval, we will find our I of t. So for the first interval, our I of t is 5 into 10 to the power minus 6. Because we are given C as the 5 microfarad. And then when we find out the differentiation of this, it should be 24 by 6 into 10 to the power minus 3, which will be 20 milliamps for 0. Now for the next part, it is minus 12 into 10 to the power minus 3, the differentiation, and it will be minus 60 milliamps and for the next part, it should be 0. So when we are plotting it, we know that we can plot it like this, that for 0 to 6, it's 20 milliamps. And from 6 to 8, it's minus 60 milliamps. And then 0 onwards. So this is your time in milliseconds. So that's how you can find current if you are given the voltage of the capacitor. Okay. Then we want to see what we have learned about the capacitor. We want to see about inductor. So we can see that too. What is an inductor? So inductor is a circuit element composed of a coiled conducting wire. Inductors are typically classified by the type of core they used. So inductor is actually a coiled wire normally. So this is the inductor picture, the most general picture of inductor, like them. And so this could be anything, core, and this core showed that it defines the ability of conductor, and the like in capacitor, dielectric defines the ability of capacitor to store the charge. Here, this core defines the ability of the conductor to store the magnetic field. Okay, and if this is your I of t, this could be your voltage across it. The circuit symbol of conductor is, we have learned about this. This is circuit symbol. Okay. So it's like you said, you see that capacitor develops a charge across its plates. Inductor develops voltage due to the changing magnetic field. So what we can say here is magnetic fields. So what I'm saying is changing magnetic field produced voltage that was proportional to time rate of change of current that produce magnetic field. So in this case, your current is changing instead of your voltage. So that's what we define, that changing current produce voltage across the inductor. Okay. So we need to define what you should say, other things as well, like the other relationships, like we have defined for the capacitor. But before that, we can just talk about the core material of inductor. So inductors, there are different cores, like you are saying that there are different core, different dielectrics of the capacitor. So core material can be air or non-magnetic material. It can be iron, it can be ferrite, etc. Okay. Ferrite core inductors are used for high frequency applications. So because they can withstand high frequency in them. And so if we talk about the magnetic lines of the inductor, they are something like that. That's the magnetic field across inductor we can see. Okay. So we have defined the voltage and current relationship in inductor. And in inductor, we say L is inductance, which is defined in Henry. Now we know that V of t is L di by dt. So I of t will be 1 over L minus infinity to t V of x dx. And if we separate this, this would be my initial condition. Okay. Then I need to know the power across power delivered to the inductor due to the voltage it develops and the current flowing through it. These expressions are almost same as what we have seen in the capacitor. Similarly, energy stored in magnetic field is and it would be so all of these things will be useful for us in case of inductor. One more thing I want to summarize in inductor is voltage across the inductor is directly proportional to the time rate of change of current. So which means we know that and if DC current is there, which does not change, so for the steady state, voltage will be 0. Which means that inductor acts as a short circuit to DC. Sounds good?
Yeah.
We actually, it's like capacitor was acting as an open circuit to DC, but inductor acts as a short circuit to DC. So I am quickly trying to solve a circuit which may help us to understand okay. I think I'm making it too big. Okay. Mm. Okay, 6 ohms, L is equals to 2 millihenry, 3 ampere, 20 microfarad, 3 ohms, 4 millihenry, 50 microfarad, 6 ohms, 9 volts. Okay, so we have to find the total energy stored in the circuit. So to find that, we need to find the energy stored in the components that store energy, right? So which are inductors and capacitors. So this element will store energy, this element will store energy, this element will store energy, and this element will store energy. But to know that how much energy they have stored, we want to know the formula, right? So which is WC of T is 1 over 2 CV square, and WL of T is 1 over 2 LI square. But to know that, what we should know here, what are the unknowns here? To find out the energy, what are the unknowns that I have to find out in this circuit?
The equivalent capacitance and inductance, and
Okay.
the total current and voltage.
Yes, current and voltage, inductance and capacitance, right? But okay, yeah, that's right. So let's say if I want to find what is the energy stored in this capacitor, I can just take the capacitor's value of this, capacitance of this, and 20 microfarad, let's say, value of this, and but I have to know what is the voltage across this capacitor, right? So I need to know this VC. I need to know this current, like the current that is flowing, the current that is flowing here, and similarly, the voltage across this. So it means that I need to know the currents and voltages across the components that stores energy, right? Okay. But I know that for steady state circuit or for DC circuits, the behavior of these components is different. So that's what I will replace, that how they should behave in the steady state. I know that capacitor will act as an open circuit, and this is, let's say, IL1. This will act as a short circuit, and that would be my current source. So I can draw an equivalent circuit like this. IL2, 3 ohms, 3 amperes, 6 ohms, and 9 volts. So this is my equivalent circuit where I am short circuiting inductors and open circuiting capacitors. So now I want to find out these currents and voltages which are required to find. For that, I can use any method because this is now a simpler circuit. I can use any method to solve it. The method I have chosen to use is KCL equation. I will write KCL equation at this node. In your book, they have chosen something different, so you can also follow that. A. So this node is A, okay? So let's try to do that. So VA minus 9 by 6 plus VA by 9 minus 3 amps is equals to 0, right? So it's not difficult. It will give me, okay, what I have done is multiplied by 9. So this is amperes just. Okay, and then so VA is 16.2 volts. Okay. So what do you think? What will be the value of VC1 here? Aiden, what do you think?
Wouldn't it be the same as VA?
Yes. So VC1 is 16.2 volts. And what will be the value of VC2?
Also the same?
No, VC2 should not be same because we have 3 ohms in the path, right? What do you think, Sarah? What should be the value of VC2 here? Are you here?
Yeah. I'm not sure.
Okay. Thomas?
I'm not sure either.
Okay. Anyone who can tell?
Is it 5.4 volts, maybe?
Why?
I just did voltage division at that node. I don't know if that's right, though.
Yes. So how you did that? How you did the voltage division? This should be 6 by 9 into 16.2, right?
Oh, I switched them. I had the 3 on top.
Oh, okay. It's okay. Yes, it should be voltage division because this is the resistors in series, right? And VC2 is the voltage across 6 ohms. So it should be 6 by 9 into 16.2 volts, which is they have given 10.8 volts. So you can check. Yes, you can check. It comes as 10.8 volts or not. However, so that's how you will find VC2. Now you know these voltages, and you can find out currents as well. So you can see that your IL1 will be VA minus 9 by 6, right? So IL1 is VA minus 9 by 6, but its direction is negative, so it should be negative. And that should be minus 1.2 milliamps. And IL2 is IL1 plus 3, because this IL1 and 3 are adding up to produce IL2. So this will be 1.8 amps. So, oh, sorry, they have in amps, so it will be in amps. Okay, so now we have these currents and voltages, so we can easily find out the energies across them. Okay. Sounds good?
Yeah. Sounds good.
Okay. Energy storage. I will find two of them maybe. So let's see, WL1. L1 is what? L1 is 2 millihenries, because I have taken this as L1. So this is 2 millihenries. So it will be 1/2 Li square 1/2 into 2 into 10 to the power minus 3 into I. This one should be IL1, which is minus 1.2 square. So that should give you, and similarly WC1, let's say, or C2, let's see, we can do that. C2 is CV squared, right? So it should be 50 microfarad into V square. V is VC2, which is 10.8 square. And that is 2.92 millijoules. So that's how you can calculate the energy storage in the circuit. Okay, sounds good? Okay, okay. And the total energy, if you want to find out, you have to add them all. Like you have to find WL2 and WC1 and then add them all to find the total energy storage by elements in the circuit. Okay, so I will do a couple of questions and okay, just a minute. So this is example 6.8. Okay, so in this, we are saying that voltage across 200 millihenry is given by the expression. E minus 3t millivolts, t is greater than or equals to 0, and is equals to 0, t is less than 0. Now we have to find out current, energy, and power. Okay. So we know that current is one over L minus infinity t v of x and dx. But we need to define it as minus infinity to 0 because we have two paths here, like the conditions we are given with respect to time, and 0 to t v of x dx. So what should I put here? Chris, what do you think? What should I put here? Here. When I will try to solve or replace things, what should I put here? Kelly's?
In that
Amanda?
section,
Yes, yes, go ahead. Kelly's, what you're saying?
in the section underlined right there, the underline.
Yes. What should I put here? If you see these two values.
What's implemented up there? We just go over to that. Wouldn't that be 0? This part.
Okay, I repeat what you're saying.
Because it's like, what is this? The first integral goes to 0. So wouldn't you just try and solve that out?
Yes, so you're saying that this is 0.
Yes.
Yes, yes, that's fine. Thank you. That's what my question was. Okay. This is 0. Why? Because you are seeing in these conditions that anything before time 0 is 0. So that's why I will put 0 here. And then I will put here the value. As I'm taking a variable x, so that's what I'm just doing x here. Okay. And 1 over L. 1 over L means 200 millihenries. So it will be 200 into 10 raised to the power minus 3. 0 to t, 1 minus 3x, e minus 3x, dx. So it's now just a simple integral question, and you can do that. So you can just separate e minus 3x dx, and you can do 3x e minus 3x dx. Okay, and that would become so this is the integral of e minus 3x. And to solve this, you will do, I think that's called quotient rule, in which you take the integral of one of them first and then take the integral of the second, which makes it, if I take the integral of this, it will make it 3x e minus 3x by 3, 3x e minus 3x by 3 minus, and then plus 3 e minus 3x dx. Okay, and then if you solve this, it should become, this is 5,000 by 200 is 5. So this should become e minus 3t minus e minus e raised to power 0 is 1, something like that. And similarly, here it will become okay. So what they have done, they take 3 out. 3x plus 1. Is it right? I'm so 1 minute. From where this 9 comes? That's why I'm wondering. Okay. Are you following this integration? Can you hear me?
We can hear you.
Are you following this integration? So if I take 3 out, it would become okay. Okay. To take yeah, okay, that makes sense. I think yes, that's fine. Okay. Okay, so you can just solve this like that. I mean, you don't have to do this. That in the book they have tried to make it looks like easier, but you can, this is also fine. You can just do that too. Okay. So but you should know this integration, I mean, how to do this integration, because that's important to solve your current here. Okay, so that should become, when you solve this, putting the values in, that should become this. Okay, and then you have 0 for t is less than 0. Then you can just find out the current and power, power by multiplying these two values, which is 5t e minus 3t, which is the current, into 1 minus 3t e minus 3t, which will become 5t e minus 3t minus 3t e minus 60. 5t e minus 3t, and no, that's not right. So that would become 5t 1 minus 3t e minus 60 microwatts. So that's your power. And similarly, your energy absorbed will be 1 over 2 Li square, which will be 1 over 2. L is 200 millihenry into I square 5t e minus 3t square, which will be 1 over 2 into 200 millihenry into 25t square e minus 60. So you know how to deal with your e's here. Then you will be able to find your energy storage and what you should say, power. Okay, so I think in this chapter now, there are more questions that we have to do than what you should say. We have most of them done in the chapter number 8, but I am just doing it to give you an idea that how these problems are. So if you have the circuit, this circuit, and you are given that you have the capacitance as 100 nanofarad with a tolerance of 20%. Then how, if this is your graph, how your voltage waveform will look like. So this is the voltage waveform graph, how the current waveform will look like. So I will show you what is the graph of the voltage. Okay, so this is 0, this is 2, this is 1, this is 2, this is 3, this is 4. Okay. So first of all, you need to tell me that if capacitor is of 20% tolerance, what values should I take to find the current when I know that current is this? So 20% tolerance means what is the maximum, like the worst values of the capacitors?
$80 and $120.
Yes. So total, like the worst values of the capacitors will be 120 nanofarad and 80 nanofarad. Why? Because it says 20% tolerance, which means 1.2, like 100 plus 20 and 100 minus 20. 100 plus 20 makes it 120. If it's 100 nanofarad, or otherwise, to find out, you can just also do 1.2 and 0.8. So 1.2 into 100 nanofarad and 0.8 into 100 nanofarad. That should give you the values of the capacitors. So you need to put these two values in to find out the current. Okay, now they have not given us the equation of the voltage, okay? We have to find out by ourselves. So this is V of t, and this is time in microseconds. So what I will do, I will find it in chunks. Like, let's say first find this waveform. How I can do that? What should be the formula for finding that waveform? How can I find out that what is my voltage in terms of equation? Yes, go ahead. Anthony, what do you think? What should I do to find this? Because if I don't have voltage waveform, I cannot solve this current. Doriel? Can you hear me?
Yeah, I can hear you. I'm just not sure what to do.
Okay, Justin, what do you think? Justin,
So not sure what to do.
okay.
Do you find the slope between time 0 and 1? So like v of t would be equal to 2 divided by 1 times 10 to the negative 3.
What formula you are using?
The formula for slope.
Yeah. That's fine. So what you said? Two. What? Sorry, sorry, you are right actually, but this is the value 3. Sorry. Yes, you're right. So you need to use the formula for slope, okay? Which is, in this case, y is equals to mx plus c, okay? Which is y is equals to mt plus c, because x is t, v of t, y is v of t, and this would be the formula. But what is m? M is y2 minus y1, x2 minus x1. What is y2? What is y2 here?
3,
3 minus y1 is?
0,
What is x2?
1,
What is x1?
0.
Yes. So this is 3 is your slope, which means that, but one thing. So the units are not same. So 3 is 3 volts, but 1 is 1 microsecond. So you can just write micro here, which makes it 3 into 10 to the power 6. Okay. So that is your V of, not yet. This is your M. So, but your V of t is 3 into 10 to the power 6 t plus c. Now you need to find c. How can you find c? So you found your slope, but you need to find c. So for this area, yes, go ahead.
You can plug in one of the x and y coordinates to find what c equals.
Yes. So let's say I take the maximum coordinates like 3 and 1. So this is 3. Okay. So V of t is 3. 3 into 10 to the power 6 into t is, I took as 1 microsecond, 10 to the power minus 6 plus c. So this makes 3 minus 3, c will be 0. So my V of t is 3 into 10 to the power 6 t. Sounds good? Are we good here?
yeah,
Okay, so now my I of t. I need to find I of t, which is c dv by dt. Now, what you should say, putting c min to find I. So it will give me I of t, c min is 80 nanofarad into 3 into 10 to the power 6 t by dt d, which will give me 80 nanofarad into 3 into 10 to the power 6, which will give me 240, and into 10 to the power minus 9 into 10 to the power 6, which gave me 240 milliamps. So I of t is 240 milliamps for 0 t to 1 microsecond, right? And putting C max to find I of t, it will be I of t is equals to 120 nanofarad into d over dt, 3 into 10 to the power 6 t, and it will give me 120 nanofarad into 3 into 10 to the power 6, 360 milliamps from 0 to t to 1 microsecond. Okay, sounds good. So now I know that if I plot the current waveform from 0 to 1, it has given me the values. So let's see. So from 0 to 1, I have 240 milliamps. Let's say this is 240 milliamps for C min, that is 80 nanofarad. So this is the current waveform, and this is the time in microseconds. But this is for C min, okay? And for C max, I have 360. So if this is 300, this is 360 milliamps for C max, at which is C max is 120 nanofarad. So that's how I am plotting the waveform. Sounds good? Am I fine here?
Yeah.
Okay. Now if you see this part from 1 to 2, we have to focus then. Now 1 to 2 is a straight line, which means that it does not have any slope, which means that it is constant. So the next part says that from from 1 microseconds to 2 microseconds, your V of t is 3 volts, right? Which makes your dV over dt is what should be your value of dV over dt? If I take the derivative of this, what will be its value will be?
0.
0, which makes it 0. So for this interval, I of t is C dV over dt, which is 0. So for this interval, either it's C min or either it's C max, my I of t will be 0. So my waveform for both of them will go here. And for 2 microsecond, it should be plotted like that. Sounds good?
Yep.
Yes. So this is example 6.10, 235 page. So now next, I think there are 2 parts of the curve again. So now you have to find out this slope, and then you need to find out from 2 to 3, then you need to find out this, and then this. And then you can plot the remaining waveform. Just make sure that you find the slope right, and then you can just plot the remaining waveform for C min and C max. Okay. Okay, I have just done the first part of it, first two part of it, because I think the slopes, you know how to find them, so it's okay. So we actually already know about this series capacitance and series inductance, but I'm just summarizing this, that what is series capacitance and series inductance. So series capacitance is if you have this circuit in which you have capacitors in series, then these are equal to, the equation is like you are treating them in parallel. And if you have inductors in series, so it's same as the resistors. And similarly, if you have them in parallel, then CS is equals to, I is equals to 1, and CI, depending upon that, this is your C1, C2, C3, Cn. Similarly, this is your L1, L2, Ln. So depending upon, this should be equal to C1 plus C2 plus C3, Cn. And similarly here, it is Ls, L2, Ln. No, that's not right. This should be opposite. So this should be 1 over Ls one over L2, 1 over Ln. So that's how you can find out the inductors and capacitors. Okay. One more thing I think we have not summarized here that we may need is that we know that voltage across capacitor cannot change instantaneously, and current across inductor cannot change instantaneously. Means that you know that they take time to build up the charge across them. So it's just not instantaneous that whenever you connect the voltage source, they just quickly develop the voltage across it. It depends upon RC in case of capacitor. So that's what we need to, and in case of inductor, it depends of L over C. L over R. So that's what we need to remember, and that we will see in the next chapter as well. So that's pretty much about this chapter, about inductor and capacitor. Some of these things we have done in the 8th chapter before, but we did not do it in terms of inductance and capacitance. We were doing it in terms of reactance. So that's the difference between them. That's what we should remember. And that's about it. Okay.
Okay.
In this chapter, you need to, and I think you, whenever you are doing waveforms, you need to know how to find out the slopes and how to do these things. Okay. So I'll just do this very, very small part of chapter 7. I'm just starting it. So we will continue it next time. Chapter 7, ENG 212. And this chapter is actually about so I want to spend maximum time on this chapter because I think this chapter is very important to do. So that's why. So let's say I'm starting from this, that if this is your circuit, and in this chapter, we will be talking about transient state, steady state, how we are shifting from transient state to steady state. And what is transient state? We know the transient state is whenever something is changing. Let's say if you have connected a voltage source to the capacitor, the time it is building up a charge across the capacitor, it's a transient state. And when it has the charge on the capacitor, it's a steady state. So that's what we need to know, what happens in the transient state and steady state. So now we know, let's say this is a charge across the capacitor is, or the voltage across the capacitor is VCT. As soon as I connect this switch, the current flows here. And the equation, KVL equation, will become KCL equation will become this, because it's the current that is flowing here. And we can write this as so how the KCL equation is becoming this, because this is I of t, which is equals to C dVC by dt, and this, the current across this is VCT over R. So that's the equation. Now, if we try to solve this equation, this will be the solution. But till now, we learned that this will be the solution. We don't know how this comes. So in this chapter, we will try to figure it out, that how this equation comes. Okay, so, and all the transient equation that we have learned. So what I'm trying to do here is have you done in calculus or anywhere else before first order circuits?
I'm not sure.
Have you
Don't think
seen
so.
this equation before, which I'm writing?
Oh, yeah. The general solution for linear.
Yes.
Yeah.
Yes, first order differential equation. So this is same as the first order differential equation. This is also this first order differential equation. We will try to find out, okay? Okay. So a fundamental theorem of differential equations states that if x of t is xp of t, so this is the general form of the equation. And xp of t to, if x of t is equals to xp of t to above equation, and x of t is equals to xc of t to homogeneous equation. So we all the time say that there are two solution to this equation. So homogeneous equation here is the equation which is equals to 0. Right? So this is a general equation. This is a homogeneous equation. And we said that the solution of this equation here is xp of t, and solution to this equation here is xc of t. So as we are doing the general form of equation, we will be writing it as x of t is equals to xp of t plus xc of t, which means that xp of t is the particular integral solution or forced response. What it means, we will learn that too. And xc of t is a complementary solution or natural response. Okay, so we need to learn that. So what it means and how we will solve that, we will see that too. But we know that general form of equation has two solutions, xp of t, forced response, and xc of t, that is natural response. So first I am dealing with the, let's say, forced response. So forced response say that if dxp of t dt plus xp of t is equals to a, where a is constant, and then this should be zero. Like if x is equals to xp of t, it gives you a forced response. If x is equals to xc of t, it gives you a natural response, which is 0. Sounds good? Have you learned it before?
Yeah, I just learned that a couple weeks ago in my one math class. I'm not sure about anyone else.
Okay. Aiden, do you know that, Thomas?
I'm familiar with it.
Okay. So I think it's just a repetition, but I am doing it because it's very important for this chapter. So, okay. So the force response says, as we know, that right-hand side is constant. So we can assume the solution to xp of t must also be a constant. So we are saying this, that xp of t is equals to k1. So when we are replacing this as a solution, we will be saying that means that k1 is a by a, because that's our xp of t. So that will make, if I'm putting it as k1, that will make it a by a. So similarly, if I just try to solve this as in terms of examining this equation, to solve this, we'll make it y. So let's say this is my 1, this is my 2. So dividing xc of t, dividing 2 by xc of t, okay, will give me this. Okay, so this makes it as okay. So I can then say that I can also write it as because this is the form of ln, that if I take derivative of ln, I will get the same thing, right? Are we following this? Are we good about this?
Yeah, I think we're good.
Okay, so this will make it okay. How I did that, I just take the integral from both sides, and this will make this as it is. And then Okay. So, which makes my xc of t as k2 e minus at. Right? Because if I take e on both sides, this will become e raised to power ln xc of t and e raised to power e minus a of t, which makes this as xc of t is equals to k2 e minus at. K2 is what you should say, any constant. Okay, so now if I see what I got here is xp of t plus xc of t, where xp of t is a by a plus k2 e minus at. So let's say if I say this is k1 plus k2 e minus at, that's my x of my solution for sometimes. So I can also say that this is my steady state solution. And this is my transient solution. But we will do little bit more digging in this, that how we will use this thing. Sounds good?
Yeah, sounds good.
Okay. So anybody who has not done this before? And calculus or differential equations? Okay, so you are all are familiar with this. So yeah, so that makes things a little bit easier. Okay, sounds good. So I think we will continue next time. Thank you. Thank you for attending it. Thank you very much.
Thank
See
you.
ya.
See
Thank
you.
you.
Bye.